Okay, let's maybe wait a couple of seconds until everyone is settled. All right. So in the meantime, we can start with a quick About Me section. So Thorsten already very kindly introduced the title of my presentation. It's about reliable machine learning. And from what I've heard from the networking before, I think it's a topic that many here are interested in. Quick facts about me. I'm Lukas. I obtained a master in computer science at Augsburg University. And now since April 2021, I'm a Ph.D. student at Technical University of Ingolstadt. And here I'm working under the supervision of Alexander Schiendorfer. So my research focus and my main interest in machine learning already since my master's time is machine learning in the context of smart manufacturing. So here in Bavaria especially, manufacturing plays a huge role in the economy. So I found the combination of machine learning and AI with manufacturing a very intriguing combination, and it's still very nice and interesting. So my dissertation topic is about reliable AI systems for smart manufacturing, and here we are diving in a bit deeper now. So in general, for my dissertation, which setup do I consider? So I consider an Industry 4.0 enabled or ready factory. So that's important. So in this factory, we have several machines that do certain production steps for goods, basically. And during these production steps, different amounts of data occur and are produced. And this is important, or here it's important that the factory is Industry 4.0 enabled because we need to get access to the data. We need sensors at the machines that record ideally as many as possible data points like temperature curves, pressures, etc., etc. And then this data needs to be written to a data warehouse, basically. So we need some data management system that records all of the data. And the use cases that I consider most are quality predictions. So either predictive quality already during the production process, so predict whether a given product is defect or not at the end of the line as early as possible, or simply resembling the final end-of-line test at the production line that basically decides whether a produced product is a defect or not and will be shipped to the customer or not. So in principle, we have defect detection in manufacturing, but also very often we have predictive maintenance. So in principle, machine learning use cases that are not especially hard to solve in theory. So most of the use cases don't require huge large language models or huge models in particular. However, we have several problems in manufacturing that hinder the adoption of AI. The first one is that many manufacturing companies, especially small and medium-sized enterprises, are still in the process of digitalization. So these companies often still face large difficulties to gather label data in sufficient quantity and quality. So setting up data pipelines already is a huge setup, a huge issue. And then if these companies have enough labeled data available in some kind of data warehouse or in a cloud system, the quality of the data and of the labels, often both, is a real issue. The problem here is that these companies often fail to establish a culture in which there is awareness for high data quality. So especially the workers directly at the production line who are working with the machines directly and putting in the materials, whatever, these guys have no data science education. So there's a complete lack of awareness that data and high quality data may be something important, and that's something we can generate value from. And on the other side, there we would need like the management of the company to establish a culture in which this is important. But that's something many companies in this sector fail, and that's a huge problem for us. And this leads us to the last problem, why the AI adoption is quite bad, often due to the bad data quality and other issues. The resulting models are often not reliable enough for real-world applications. So if we are producing something, especially in the automotive industry, then we have safety requirements. So if you produce, I don't know, parts for a brake, and this brake is then mounted to a car, then you have very hard safety requirements that this part needs to be 100% okay. So reliability is a huge problem for us. So reliability and trustworthiness are terms that are often used pretty much in exchange, and I want to explore the connection between these two terms first. It's quite hard to find a very exact definition of trustworthy AI and reliable AI. Sometimes both terms are used interchangeably. From my understanding and how I've seen this topic in the last 4 years is that reliable AI is basically a subset of trustworthy AI. So reliable AI is a very important aspect of trustworthy AI, but the term trustworthiness includes many aspects that are not really relevant for reliable AI, in my opinion. So reliable AI includes terms like well-calibrated models that are not too overconfident, models that are dependable, models that are robust if the data changes slightly, continuous learning, and also the term that I really like is uncertainty communication, so that the model communicates when it's not 100% sure about a prediction. But trustworthiness, in my opinion, so this is maybe a bit personal, also includes like or especially includes the human perspective, the human-centered perspective. So like fairness, trustworthy AI systems should be privacy preserving, they should be unbiased and explainable. So the explainable or explainability requirement is something that we often get to hear from manufacturing. But I still wanted to focus in my PhD on the reliability aspect because in the end, so the reliability part is the one that is integrated in the production pipeline in the end. So when we don't want to get human feedback every time the model is unsure about an instance. So how can we achieve reliable machine learning systems? And this list is absolutely not exhaustive, but I want to give you a brief overview of how this could be achieved. First of all, when we have trained a machine learning system and you want to make sure that it's reliable, you of course first need to get an understanding of the data and label quality. So we need to make sure that we may be aware of any issues we have in the data set. So sometimes labels are put into both defect and okay folders for some reason. So we need to get ahead of these issues, so to be aware of it, so that this could be a problem. Then, of course, we need to ensure absolutely proper testing of the model under all requirements that we have in the real deployment. And we also need to have a very good understanding of the model's performance under different conditions. And that's especially important in the manufacturing industry because often the production processes are highly dependent on the surrounding conditions. So for example, if some parts are glued, so with some glue, the process behaves very much different in summer when the production building is much warmer than in winter. So we need to make sure that our model is able to handle these changing conditions as well, for example. Also very important to ensure reliability is to make sure that the model is well calibrated. So it shouldn't be overconfident in its predictions. So like the speaker before me already mentioned, the large language model is also always very confident in its prediction that it's really this diagnosis and offers no uncertainty measure. And here it's for reliability, I think it's important that the model is not too overconfident. But what the approach that I like best, basically, because it gives us something that we can quantify, is the uncertainty estimation. So here we want to communicate if the model is certain or uncertain about the prediction. And very early in my PhD journey, I discovered that this is the direction that I like most and that I can or get the best feeling for reliability in manufacturing. So methods for uncertainty estimation, there exist tons of different methods for uncertainty estimation. I grouped them together into 3 very rough groups, and of course this is as well a non-exhaustive list. But of course the the true way, or the maybe best way to build models that can estimate their predictive uncertainty are Bayesian methods. So here we build an inherently probabilistic model, for example, the well-known Gaussian processes, or Bayesian neural networks, where we basically use probability distributions instead of weights, and then we get an output as a probability distribution, not as a single point estimate. But especially Bayesian neural networks are still they are still evolving, and in a relatively early stage. We have very few well-working frameworks for it, and in general, the computational feasibility is difficult. Then an approach that gets much attention in the last couple of years is so-called conformal prediction. Here we build a so-called prediction region around the prediction. So for example, in multi-class classification, we offer a set of predictions, and this set of predictions contains the correct one with a certain probability, for example, 95%. Here we basically get a measure of uncertainty by the size of the region. So if the region is very large and contains many classes, then the uncertainty of the model is, of course, higher than if the estimate only contains 2 different classes. But conformal predictions is something I also struggle to apply to defect prediction in a meaningful way, because in defect prediction we have binary classification. We only have 2 classes, defect or not. So and here the meaningness, or the meaning of the prediction region is a bit lower than, for example, if you consider like these 100 or 200 different diseases, or if we consider ImageNet, the ImageNet data set with 1,000 different classes. So there, the prediction region is much more meaningful compared to binary classification. And in the end, that's why I always stuck to ensemble-like methods. So here we either build or simulate an ensemble of models, for example, random forest or Monte Carlo dropout, and we calculate the variance of our estimated or build ensemble to estimate the uncertainty. So if the individual ensemble members disagree with regards to the prediction and predict very different values, then we get a feeling for, okay, maybe this instance is not as clear as we wish. And here, especially with Monte Carlo dropout, I want to dive a bit deeper. Monte Carlo dropout is one of the most widely used uncertainty estimation techniques for deep neural networks. It is already well established. It was proposed by Yarin Gal and his colleagues in 2016. And but in my experience, it is still a very robust mean of uncertainty estimation. It works usually as intended. And since most neural networks are trained with dropout, it's very easy to achieve. The basic idea here is that we leave dropout on during evaluation. So usually when we evaluate our model, we turn dropout off. But here with Monte Carlo dropout, we leave the dropout layers activated. And since dropout randomly drops connections between 2 layers, when we let the model predict the same instance n times using dropout with dropout activated, we get n slightly different model architectures. And here we can simulate then a very small, or more or less small, ensemble of different model architectures without the explicit need to train multiple model architectures. So with smaller, especially classical machine learning approaches, it's not too much of an issue to train multiple runs of a model, but with neural networks where the training times are much higher, we want to avoid multiple training processes. And with this, we can only have one training process and still simulate an ensemble with n slightly different model architectures. So much for the theory. I now want to get into a small case study based on a paper of mine from last year. Here we used uncertainty estimation to reduce the usage of large models in a cascade. So let's explore what this cryptic title means. The setup that we considered in this paper is quite similar to the setup I proposed in the beginning. we again have a production line with multiple machines, and these machines generate data, and we want to do quality predictions. And here we assumed that in a smart factory, we have roughly 3 abstract levels of compute devices with different capabilities. First of all, in the lowest tier, we have edge devices. These edge devices are very close to machines, but have limited computational power. Then we have the intermediate layer. Here we have solid computational power, for example, on a workstation. So a workstation can get quite beefy. But maybe the computational power is not enough to solve all tasks in sufficient and in sufficient quality, basically. Then usually every manufacturing company now has access to some kind of cloud environment, whether it be a local data center of the company or a hyperscaler where the company has a contract with. Here we have nearly unlimited computational power, so we can use the best possible version of model that solves our use case. But we have, especially in the manufacturing industry, privacy concerns with the data. And in the last couple of years, the prices for cloud computing grew into, not infinity, but into heights, definitely. So that's something that we want to reduce. We want to calculate less inside of the cloud or largest instances. So the 2 tasks that led us throughout this paper journey was how can we assign the compute task in a way that minimizes the use of our largest model? In other words, how can we use our largest compute device much less while still maintaining the same predictive quality? And in the same turn, how can our AI system be reliable? So how did we solve this? Here comes the ominous cascade into play. We built a small cascade, in this case, of 3 different models for the 3 different compute tiers. And the basic idea here is, can we separate instances into 2 classes, easy or hard to classify? And always easy or hard to classify for our current tier of compute device. And the idea here is if some instances are easier to classify than others, then for these easier instances, smaller models are sufficient to classify these instances in a reliable fashion. So the basic idea here is that we always start in the edge layer and with the smallest device. And if an instance is very easy to classify so that the computational power of our edge device is already sufficient, then there's absolutely no need to delegate the decision to the 2 upper tiers. Then we can directly claim, all right, this prediction was certain. No need to calculate any further. Then we have our accepting state here. However, on the other side, if the edge model is uncertain about the decision, we delegate the prediction to the next upper tier. Here, the same play. If this model is certain, then we put the decision into our accepting certain state. On the other side, if this intermediate model is uncertain as well, we delegate it to our most powerful model. And if even this model is also uncertain about a decision, then we need to either hand it to a skilled worker and have some manual inspection, or we need some special quality control for these instances, for example. But the borderline is here, if even the largest model is uncertain, then we need to do some appropriate measures to get an insight if this product is defect or not. So and that's how we can combine the uncertainty estimation and the reliability into one approach. How exactly can we distinguish between easy and hard instances using uncertainty estimation? We use a mechanism that's called selective classification, also a well-researched approach. In principle, here we follow the notation of Geifman and Elyanev. Basically, for each model type, for example, support vector machine or neural network, we define a so-called selection function. And this selection function then observes the model during its prediction, and it basically decides if the model was certain or uncertain during the prediction process. Here, as I already mentioned, we need a specific selection function for each type of model. So support vector machine behaves slightly different compared to a neural network, for example. So we need different selection functions here. But how these selection functions exactly look like, we'll see later. So that was the reliability part. how can we actually connect these models in our cascade? So, as I mentioned, the models are deployed on different compute devices, and these compute devices are, maybe even in physically different locations. To connect these models, I settled for Apache Kafka as an interconnect. So Kafka is very fast, it's open source, and it's already widely used in the manufacturing industry, especially for sending the sensor data to the data warehouse. So there are several approaches that already use Kafka. How exactly do we use Kafka to connect these two models or two nodes in our cascade state graph? If we consider a state transition from A to B, here we model the state transition by creating a producer for the sending state and a consumer for the receiving state. And between the producer and the consumer, I created a connecting topic. So the producer, whenever some data is ready to be written to this topic, writes into this topic, and the consumer, for example, the model in the next upper tier, always listens for new data to be sent to this topic. A couple of details for the interested here. The images here are serialized using Pickle, so like the easiest possible approach, but it worked surprisingly well. The individual applications, so like the application running on the edge device, on the intermediate and on the cloud device, and evaluation and data producing processes, these are all asynchronous applications. And I implemented these applications with a library that's called FastStream. It's open source on GitHub. It has, I think, 3,000 stars already, so gained quite a lot of traction. And it's a really nice library because it allows you to build these asynchronous applications without much effort. So it's like, I don't know, I think the average lines of code per file and per application was, I think, 50 or so. So really short applications and nicely written. Each inference application first reads from the topic, deserializes the image, applies the necessary transformations, so depending on the model, and then performs the inference. After the inference, we perform our uncertainty estimation mechanism, and then depending on the result of this uncertainty estimation mechanism, we either write to the next topic for the next model, or we send our decision to our final decision topic. Yeah. So that was a lot of theory. Now let's jump into the experiments. So how did we evaluate this cascade? And here we settled for a prototypical industrial defect detection use case. And here we settled for pictures and images. We have used a data set that contains solar cell images. And the issue here, or the problem here, is simply to predict whether an image contains a defect or not. So if, for example, here we see very clearly that this solar cell has a defect because it has massive cracks inside. And I chose this data set because it's very prototypical for industrial quality assurance applications. And it also had a couple of nice other features, but that's described in the paper. So which models did we use for our different tiers? So I actually settled for the edge device with a support vector machine, so very classical machine learning, but for resource-constrained devices, the support vector machine is still a well-working approach, and especially if we look a bit in the collection of different descriptors for the images, there are still a couple of interesting ones and that are also well-performing. And we actually found that the accuracy that we lost here was not as, or didn't took a hit that was as big as expected. I used the DAISY descriptor. The descriptor is implemented in the scikit-image data library. So if you want to do image processing or image recognition, the scikit-image library is a very good find here. The support vector machine is like the standard one from scikit-learn. As a medium model, the problem is not too complex. I settled for a Linnet-style CNN, very easy or very basic 5 conf layers, 2 fully connected layers, quite small. And then for our largest model to simulate for this problem, I used a pre-trained CNN from the Torch Vision Model Zoo. I used the MobileNet version 3 large variant here. And for my 2 neural networks, all of it is implemented in PyTorch, and I trained it with the help of PyTorch Lightning, which is definitely a very nice library for training neural networks. So let's take a more or less deeper look into the selective or the selection function. So how did we estimate model uncertainty? And here's another argument for the support vector machine. It's very similar to the mechanism before inside the embedding database, where we can calculate the distance between the embeddings. The support vector machine tries to fit a hyperplane between the 2 classes. So the goal in the support vector machine is to maximize the distance of the hyperplane to the 2 classes. So we can basically assume that if an instance is very far located from the hyperplane or from the decision plane, then this instance is much more certain than, for example, this instance here that is quite close to the hyperplane. And we estimated also a threshold in experiments upfront. Then for the medium and large models, here we use the Monte Carlo dropout method again, and we aggregate the predictions of the ensemble members and measure the variance and also combine it with the raw model confidence. So here we played around a bit. So how much did we gain, or how were the results? First of all, the main question, how much can we reduce the usage of the largest model? And our experiments showed quite a nice result. We had, in this case, 522 instances overall, so small test set, but the data set itself is not large. And we see that only 47% of all predictions were performed by the largest model. So that's a reduction of over in half. And if you assume that, this model runs on an AWS instance, then the utilization of this instance is reduced by a half. And I think that's quite a nice result. But how much performance do we lose by doing so? So now we are doing more predictions on smaller and less capable models. And here we see that our hit in accuracy is actually not too bad. So we lose about 1.5% of all of accuracy. But since we also applied uncertainty estimation mechanism, it was fine. In this particular use case, we had a bit of problems with defect detection, but that was not the main goal of this project. So it's definitely possible to keep the accuracy loss at a okay-ish level without sacrificing too much of reliability. So that's the bottom line here. And also, since you may think sending images using Kafka is not the perfect idea, that's something I also worried about before, but the maximum message size in Kafka is 1 megabyte, and our average image size was about 88 kilobytes, so still very far away. These images weren't too large, so it was fine. What about the latency when we connect all of this together? We only did a very, very rough proof of concept test setup inside our university building. I used this crappy laptop that nearly died while using Adobe Reader, so really by far not industrial means, and 2 workstations and our more or less well-working university network. So really just a proof of concept setup, and we were able to process about 10 images per second. And I think that's already a value that can be used in practice, basically. So you first need to find a production line that has more production steps per second. So I think, and that's definitely something we can improve. And compared to the largest model, so what about when sending everything to the largest model, then the value stayed roughly the same. So we didn't sacrifice any performance here or any latency here. So overall, I think that it's quite a nice result. We could reduce the utilization of our largest VM, for example, while making reasonable sacrifices in accuracy. So, and now thanks for your attention, and now open for questions.